So, good morning and welcome to this new example of ORTools. My name is Frank. It has been a while that I shared the video with you the last time. Since then, there have been quite some good developments within MTEX and ORTools, so it's about time to maybe make a new video and show what we've been up to in the meantime. Today, we're going to look at an example on habit plane determination from 2D orientation maps. And I've already run the beginning of the code to get the reconstruction of the lath martensitic microstructure to an austenitic microstructure, and the result looks something like this. If you've never done this before, I would recommend you to look into the examples on the variant graph, which I think is example number 7, where I will guide you through how to do the parent graph reconstruction. But to not do so much redundant content here, I would just like to start up from this point right away. So this is example 9 we're running. I've been running it onto the reconstruction part here where we merged similar grains and we merged the inclusions and we created the EBSD data and then plotted this. Maybe to show you, example number 9 can be found here on our webpage, github.com ORTools for MTEX or ORTools, and there's also an example 10 that I will talk about soon. To run this code, please get the latest version always of ORTools and of MTEX. So right now I'm running ORTools 2.2.0 and MTEX 5.10. So the next part in this code would be to calculate the variance. So we just done the parent graph reconstruction, right? So now we know the parent orientation, we know the child orientation, so the austenite and the martensite orientations, and from this we can calculate the variance. So we can run this, we can mark this stuff and click F9 to run this command, and we can see the variance are calculated. Nothing's really outputted because the next 3 commands are there to give us some graphical feedback. So the first command here is plot map variance, which will show a map of the variance, how they're distributed in the reconstructed microstructure. Here we also get a visual output in the command window where we get the area fraction of the variance in our map as well. So we have 24 different variants, as we can see. So this is the variant map. We can see the outlines of the austenite grains, and we can already see that there are some different packets where similar variants are paired together. But we can also plot the packets themselves. So here we're having the packet map. We have 4 different packets, and per grain we maybe have 2 to 3 packets we can see. And then at last we can also plot the Bain groups, which is a new feature we've recently implemented. So this is the plot of the Bain groups. Note that we also implemented some new color maps recently, so there are a lot of different color maps that you can choose from. You can see about this in the documentation, and this is just an example of manually specifying which color map you want to plot. So you can also provide this extra parameter color map to the plot map packets and plot map variance commands as well. So these are the Bain groups. So this has basically just been a small warm-up exercise because the habit plane determination starts now. So the habit plane determination is put into this block here, and it's just a few lines of code because most of the brain work is of course put into MTEG and then also put into this command compute habit plane. We put a link here with the research paper where we talk a little bit about the methodology. I thought I would probably guide you a little bit through this paper to tell a little bit about what habit plane determination is about and how the algorithm actually works under the hood. So this is the paper. As noted, it's put onto the ORTools repository under doc, and then it's called this. So for some of you, this might already all be very well known, but I will go a little bit into detail for people who are new to habit planes. So when we have a phase transformation happening in our material, we usually have a parent phase and then we have a child phase. So one is the phase that we have to begin with, and one is the phase that's being transformed into. In this schematic here, we can see we have this parent face in red and the child face in blue. And of course, those faces, they have different crystal lattices, they have some orientation relationship, and they also have an interface with each other, where the two different crystal lattices meet. Usually those interfaces are having some kind of close packed relationship, so that in this case the close pack 110 plane is parallel to the 111 plane in the parent face. But what also happens is that due to the accommodation strain of, let's say, the different volume and the shears involved in the face transformation, we get some curvature into this macroscopic interface. So atomistically, we have ledges of very nicely arranged interfaces with a low energy configuration. But macroscopically, those ledges here, those terraces of different atoms, they show up in a macroscopically visible interface that is different from this perfect crystallographic interface. So this green line here indicates actually the habit plane. And this is when we do, for example, an EBSD scan, or we go to the transmission electron microscope, is what we perceive as the interface between the two faces. So of course, this habit plane is a plane, it's a 2D object, and when we do a orientation map, we can only see lines which are the traces of this kind of interface. So we cannot just do an EBSD orientation map and directly deduce the habit plane. But of course, through the magic of parent grain reconstruction, variant analysis, these things, we know a lot about the relationship between the parent and the child face. So we know a lot about also this orientation of this trace within space. And if we have a lot of these traces, we can actually deduce the habit plane. And this is what we set out to do in this work. Yeah, there's of course a lot about the theory, which I'm not going to go into. I'm just going to go a little bit through the figures here. So we have this figure 2, where we show some different stereographic projection of the traces. So I just showed you earlier what the trace looks like. This was the green line between the two faces. Now, if we have a big orientation map, let's say of lath martensite, and we determine the traces as the long axis of all the grains, right? Then we could plot those traces into a stereographic projection. And if we just do this right away, this will look like figure 2a. So in this figure 2a, the traces are basically shown in the specimen's reference frame, right? Because that's what we usually do when we determine the traces. We determine the traces of the habit plane with respect to the specimen coordinate system. And we can of course see that all of those traces are lying within the x and y plane. What we can also see is then in figure B, if we then just take those traces and rotate them into the parent reference frame, we get those semicircles rotated in a way that we actually take the surface of our orientation map and rotate them into different crystal reference systems based on the orientation of the parent face. So that just means that those semicircles are rotated into different configurations. What we are missing here is, of course, to also take into account to which variant this trace forms, right? Of course, we can rotate into the parent grain, but the variant of the martensitic grain also has a certain symmetry towards the parent face, and this is currently not respected. So here's, of course, where parent grain reconstruction comes in handy, because we also know the variant. And if we then look at panel C, if we just apply all the different crystal symmetries for all the different variants, we get this figure in crystal C. We of course get a lot of points then with 24 variants, but we can already see that there's some pattern in this curve, in this plot. What we can see is now that we applied all possible symmetries. Of course, we therefore don't get a unique plane in any way. But if we then, knowing the actual variant ID, only use the symmetries that are associated with the certain child variant, then we get this semicircle here in panel D. And this semicircle shows all the traces of all the variants that were rotated into the parent and then into the, let's say, into the right variant ID. And in this way, we get a semicircle of traces that all lie on the same plane. So if we fit a line through all those traces, so we find the best perpendicular direction to all these traces, then we actually get the habit plane. So if we know the traces and we treat their rotation right, we can actually then fit the habit plane in the end. and this is what we're doing in this work. There are some different ways of determining the traces. We designed 4 different algorithms, which I'm not going to explain detail here, but just shortly, we have the Fourier algorithm, where we look at pixels within each pi austenite grains that are associated with a certain variant. So here we have 2 different variants highlighted, and by looking how those pixels are distributed in, let's say, long segments, we can then, by the characteristic Fourier spectrum, fit an ellipse to this and then determine the long direction of those features. Similarly, we can look at the radon transform. The radon transform also looks at the image pixels. So here we go. And this way we can also find the long axis of those features. Then we also have two ways of looking at grain-based trace determination. So here we actually look at the grains of each variant within each parent grain. And we can make a circular histogram, and then of course we can figure out that the boundary length in one direction is longer than the other direction because we have those elongated features. And by this way, by fitting this nicely, we can figure out the long axis of our structure, and the traces they are shown here. And then, of course, also in number C, we have something called characteristic shape, which is similar to this histogram fitting, but it's a little bit more robust. And those grain-based methods are also pretty fast. So with that being said, I don't want to dwell more on the theory. You can read the paper if you have time and interest. So now we're going to look into how to actually compute the habit plane. So we have this command here, compute habit plane. We provide the parent grain reconstruction job. Then we have to indicate which kind of method we want to use to determine the traces. In this case, we specify the radon method. We give a minimum cluster size. As shown earlier, within each parent austenite grain, we look at the pixels of each variant. And of course, if there's only very few pixels there, it's very difficult to determine any type of traces. So we kind of say at minimum we need 50 pixels to do anything. And you can set this depending on the microstructure that you're looking at. And then the last command is plot traces. Mind you, if we're looking at, especially when we're looking at the pixel-based algorithms, the plotting is a lot. So if you're interested in looking at your results, plotting is encouraged. If you want to do this more routinely, I would actually leave out this comment, this parameter, to speed up your calculation. So what we do is we just mark this, push F9, and then we wait for it to finish. So we've now gotten all our results here, plotted in all those tabs. There should be 4 figures in total. Let's start with this one. These are the fitted traces, right? And we can see that for each variant we have 1 figure, which can make this a little bit tedious to plot. Let's maybe have a look at some different variants. So here we have this, parent austenite grain structure shown by the outlines of the grain boundaries. And then we have some grains, only some as you can see, where we actually plot variant 18 and we plot a trace. This is of course due to this criterion that we set, minimum cluster size. So a lot of those smaller grains or grains that are oriented in a certain way are not going to show up enough of this variant 18 to actually allow fitting of the trace. But we can see that in the grains where we do have a trace, we can by eye kind of, let's say, identify this elongated direction of the microstructure, and we can see the trace that has been fitted using the radon method. And I think we're quite happy with the results. And this is of course done for each of the 24 different variants. So once we've fitted all those traces, we can of course plot them into a figure. This has been done here. We enlarge this figure. So what we see here is of course the pull figure of the parent phase, and we can then see all the traces that have been rotated into the parent crystal crystal system as well. The gray ones are discarded parent traces, because one parameter that you do not see when we call a function right here is that there's also a reliability parameter, and the other two examples this has been set. By default, this reliability parameter is at 0.5. You can of course edit this if you're not happy with which traces are discarded and which one are actually used for fitting of the habit plane. But yeah, here it's the standard of 0.5, and the research paper shows you how this metric is calculated. It's different for each of those trace determination algorithms, and it basically gives you reliability of how reliable do we think this trace is. So then all the colored dots here, they are different trace directions, and if we then find the direction that's best perpendicular to that trace, we get this red line here, and the pole of that red line is given down here together with the habit plane, which is yeah, close to 111 basically. Then we also have another plot that shows the same thing as a contour. And here we can see that we actually have a lot of traces around the 101 pole, which is something that we've consistently observed in martensitic steel microstructures, and we're still looking into where this originates from. Oh yeah, this is basically the same plot as you've seen before, just using a contour of the analyzed habit plane traces. And then we also have this last plot, which is the habit plane traces of the determined habit plane. So now we can do a similar plot again as for the habit plane trace fitting. Just in this case, we can take each grain, we can plot all the available variants, so not only the ones that are at least up to the cluster size, and we can then plot the trace of the determined habit plane alongside of that. And we can see in most cases it fits quite well. Notably, it doesn't fit for every grain, at least not visually. But yeah, it's an average habit plane, and also sometimes it's quite difficult to see what is the long direction of each grain. But on average, I think it is a quite good agreement. Of course, we plot this trace into each of those grains, even those that don't contain any variant. But this is kind of a sanity check for you to see, okay, does the habit plane that I calculate actually align well with the microstructure that I have? So those are 4 visual feedbacks that you get when you choose this option plot traces. Now let's maybe briefly close the figures to give the computer a little bit of breathing space. So the next thing would then be the compute habit plane commands together with the shape approach for the trace determination. So the shape approach is the characteristic shape that I showed you earlier. That is a grain-based method. So here the plotting is going to look a little bit different than for the pixel-based. It's also going to be a little bit faster, even though it's still quite involved. But you can always remove this plot traces. And here we give the reliability index of 0.5. This is also the standard, so it's not really useful, but we usually use these scripts to show you a little bit of which parameters you can actually set. So again, with F9 we can run this, and then we wait for the plots to finish. So the results have flown in. The plot here is going to look a little bit different. This has to do with that we're now looking at a grain-based method. That means that we actually can plot all the fitted traces on the grains themselves, which is a little bit more convenient than in the pixel-based or EBSD data-based method before. So here we can again look at the fitted traces using this characteristic shape method. And I think it looks quite good. It seems that the traces represent quite well the long direction of the grains. Then we again have the same plots for the spherical projection of the habit plane traces, and also this kind of contour plot. And we can see the result is pretty close to what we had before using this different method. So then in the end we can also plot the habit plane traces of the determined habit plane. So this is the average habit plane that we determined, and the traces that are associated with this on top of all the grains. And again, by majority this fits quite well, but you might also notice it doesn't really fit on every grain. This could mean that we actually locally have different habit planes. It might also mean that this 2D cross-section that we get sometimes gives us a little bit misleading idea just by eye where the habit plane is. So this is maybe in the eye of the beholder, but on large this fits quite well. And here we also get an additional figure that kind of shows us, okay, where does the fitted habit plane trace actually deviate highly with the determined habit plane trace. So the one that we actually fit onto the grain, or determine from the grain, how well does that align with the one that we get based on the habit plane that we fit in the end. So this is the angular deviation. We can see that some grains are horribly off, but most of the grains have quite close agreement with this average habit plane that we determine. Here maybe I also have to state that this example that we've chosen, lath martensite, with this very, very coarse map, is probably one of the most challenging examples that you could choose. So for a lot of microstructures, for example, as plate martensite, this is going to look a lot cleaner and more determined. So it's actually a quite difficult example that we're looking at. And in light of that, the results are pretty good. So as a next method, we can also use this histogram based method where we look at the circular histogram of the grain boundary length that I showed you earlier in the paper. We're just gonna let the plots finish here. So I will not in detail go through all the plots again because they're quite in line with what we saw before, but here are the final traces that are associated with the fitted habit plane plotted on top of the microstructure. The coloring, by the way, here is the variant coloring, so each variant has its unique color. And this is an example of then actually choosing an individual color map, which is jet in this case, and the line color white. The line color determines the color of the traces. So you also have some, let's say, freedom in defining how you want this plot to look like. The last example is going to be a challenging one because I want to show you that we actually can also determine the habit plane only looking at one single prior austenite grain. It's challenging, but it's doable. For this, we determine the grain prior austenite grain with the biggest area. So this is the index we get of the maximum grain. And then we just provide this parent grain ID parameter to the function to say which grain are we looking at. That's basically it. We give a minimum cluster size of 20 here, and we use the caliper method, which is basically the simplest method you could think of to determine the traces of the martensitic laths. So let's run this and wait for the plotting. So there are several interesting things to look at now. So these are the traces that have been determined in this prior austenite grain, right? And just visually it looks quite good. Then if you look at the next figure, we can see that we of course now only have a few traces to work with, but we can still actually fill up the entire bandwidth of this plane. This has to do, of course, with that we look at different variants which have their own symmetry. So by rotating them around, we actually populate this spherical projection quite well to actually do a fit. Then we actually kick out a lot of the parent traces as discarded. Even though they still look quite good, so probably we don't need to be that rough on the reliability index. We could probably reduce this a little bit, but anyway, just using a few traces, we then get a habit plane, which is quite close to what we had before as well, using the entire data set. And then we also fit all the traces that are associated with the habit plane, and we see that this actually looks quite good. So even only having one parent grain, and there might be reasons why you have this. Maybe you have a TKD data set, for example, where you only manage to map one parent grain. Or maybe you want to look at a specific parent grain or the difference between different parent grains. This can actually be enough for you to get a good habit plane determination using the algorithm here. So as a last thing, we can now also compare the different habit planes that we got from the different methods in an inverse pole figure. For this, we wrote this short code here. So we didn't make our own function for this. This is just something you can edit yourself to then kind of give an overview of your analysis in the end. So this is yeah, the fundamental region, right? And here we have the different results. So the 111 direction is just giving as a reference because we know that all of those habit planes are quite close to 111. And then we get the habit planes determined with the different methods right here. We can see that the shape and the histogram method, they are quite close to each other because they're also quite closely related with each other in the way they're built. Then the radon method is also quite close to those two, and the caliper is slightly further off, but really not that far off. So they actually quite agree quite well, all those methods that we've implemented. And of course, in the paper, we've also, in a research paper, we've also looked into how accurate are these methods in quite a lot of detail. And it seems that they're quite robust, even comparing to a known habit plane in 3D. So if you want to know exactly how far these points are away from each other, you can always take the output here, habit plane 1.parent. This actually gives you the HKL. And then determine the angle. So here we do, for example, angle between habit plane 1 parent and habit plane 2 parent in degree. We push enter and then we get, okay, habit plane 1 and habit plane 2, which were radon in shape, they are like less than a degree away from each other. Then we can, for example, look how far away is actually habit plane 4. This was the one that is done on a single grain from this habit plane 1, and this is also just about a degree. So they're all quite close to each other. Yes, so I think this concludes this instruction on the habit plane determination example. We might still edit this a little bit in the future, but this is basically where it is. I think the visual output is now very compelling, and it helps you to visually check your results if you actually think you're close to the habit plane or not, because if you only get a number in the end of the day, you don't really know if the algorithm was robust or not. So I think this helps you to actually yeah, put your results into perspective. And yeah, I hope you enjoy the feature and you can do a lot of interesting research with it. See you soon.